Myself, Dr. Somir De, teacher in charge and assistant professor of mathematics section under Department of Basic Science and Humanities, Asansol Engineering College. This is lecture number 5 under module number 1. Topic is improper integral under module calculus integration. Paper name Mathematics 1A and paper code BSM-101. This subject belongs to BTech first semester Computer Science and Information Technology. Introduction. Definite integration has many limitations. First, for definite integration, the integrand has to be a bounded function over the domain of integration. Second, the limit of integration have to be real numbers. That is, the domain of integration has to be bounded interval of R. Attempt to define integration over unbounded interval and also to unbounded integrand has been successful. Such integrals are known as improper integrals. Improper integral, two types, type 1 and type 2. So here we want to discuss type 1. Improper integral of type 1. All improper integrals are divided into two types. The first of which has unbounded intervals as its range of integration. We have three cases. Unbounded means, suppose you can check, one is infinity. If you have, you can consider this is one improper integral of first type. So that means if anywhere you can see, anywhere, that is your range of integration. Suppose a to infinity, minus infinity to a, or minus infinity infinity. So that means if your integration range is associated with the infinity, then this is called improper integration of type 1. Improper integral of type 1. Clear? So first one, that is a to infinity, that is your upper limit is infinity, fx is defined. This integral is defined as limit x tends to infinity a to x fx dx, provided the integral a to x fx dx is defined for every x greater than a. So that means if your limit is associated with the infinity, then we can express as a limit form. Now try to understand with example. Evaluate 0 to infinity e to the power minus x dx. So 0 to infinity e to the power minus x dx, you can write limit x tends to infinity 0 to x e to the power minus x dx. So e to the power minus x is equals to minus e to the power minus x, 0 to x. So it means that is upper limit, that is minus 1 minus 1 by e to the power minus x. What you are doing, ultimately what we are getting, very simple. After simplification, you are getting that is minus of e to the power minus x minus e to the power 0 means 1. So ultimately you have e to the power minus x. So e to the power minus x goes to 0 as x goes to infinity. So that's why, so you have this portion is 0. So 1 minus 0 is equals to 1. So this is the solution of this question. Next, minus infinity to a, second type. Under improper integral of first kind, this is type 2. Minus infinity to b fx dx. This integral is defined as y infinity y to b fx dx, provided y to b fx dx is defined for every y less than b. Very simple example. Try to understand. Minus infinity to 0 to the power x dx. So this can be written as limit y tends to minus infinity, that is y to 0 e to the power 2 to the power x dx. So 2 to the power dx limit y tends to minus infinity to 2x by ln x, that is y to 0. So that means upper limit, that is 1 2 to the power 0 by ln 2 minus 2 to the power y by ln 2. So 1 y tends to minus So that means this portion goes to 0. That is 0 by something means 0. So ultimately you have 1 by ln. So from it is clear, if your integration range is associated with the infinity, maybe upper limit, maybe lower limit, you should convert as a definite integration form, and those infinity can be expressed as a y or x like this. Next, minus infinity to infinity fx dx. This integral is defined as minus infinity to m fx dx plus m to infinity fx dx, where m belongs to r. So from it is clear, if you have a minus infinity to infinity, so that means this expression can be expressed as a type 1 and type 2. So this is your type 1 and this is your type 2, where m belongs, so that if the integral and integral minus infinity to m fx dx and m to infinity fx dx are defined as per the above definition, then the above integral is defined. Thus, from by the definition, minus infinity to infinity fx dx is equals to limit y tends to minus infinity y to m fx dx plus limit x tends to infinity m to x fx dx, where y less than m less than x, provided y to m fx dx and m to x fx dx exists. Now try to understand with some example. This is very good example for you. So from it is clear that minus infinity to infinity you have. So this is the improper integral of first kind. This is type number 3. So you have a minus infinity infinity. What is your middle point? 0. So you have to divide this. First you have to divide. If I write, if you want to add some line, you can add, sorry, so if you want to add, you can write it, no problem. Like, so what you have that is minus infinity to 0, 1 by 1 plus x square into dx plus 0 to infinity 1 by 1 plus x square into dx. Okay, then you can write, so this is your first type. So this is your first type and this is your second type. So that means this first portion you can write y limit y tends to minus infinity y to 0 dx by 1 plus x square, and limit x tends to infinity 0 to x 1 plus x square. So limit y tends to minus infinity tan inverse x y to 0 plus limit x tends to infinity tan inverse x 0 to x. So ultimately what you have, limit y tends to minus infinity 0 to tan inverse y plus limit x tends to infinity tan inverse x minus 0. So when you are considering y tends to minus infinity, so that means you have minus of minus pi by 2. And here tan infinity and inverse infinity is a pi by 2. So ultimately you have minus of minus pi by 2 plus pi by 2 is equals to pi by 2. This also very important examples for you. So from here it is clear that improper integral in first kind, and in first kind there are 3 variations you have. There is a upper limit infinity or lower limit infinity, or upper and lower limit both are infinity type. There is first part a to infinity, second part minus infinity to a, third part is minus infinity to infinity. So similar type of question try to solve from the book. Now, so this is also very important part. Improper integral of type 2. So here also there are 3 possible cases. A to b fx dx, where fx is unbounded only at a. How to decide unbounded? Very simple, where you can see when you put x equals to a in fx, your fx become undefined. Fx become undefined. Okay, so fx become undefined. Then this improper integral is defined as a to b fx dx is equals to limit epsilon tends to 0 plus a plus epsilon b fx dx. A plus epsilon b fx dx is defined for epsilon is positive. Try to understand. So if your function is unbounded only at a, so you can't substitute the value of a. So that's why what you are doing. So that means a plus epsilon means what? You are suppose your function is defined, this is a and this is b, but you, at this particular point your function is unbounded. Then what do you do? So your integration should be from here, that is a plus epsilon. So when this a, what is epsilon? Epsilon is a positive, close tends to 0, then your a plus epsilon coincide to a. Okay, where epsilon is a positive number. Try to understand with some example. So evaluate 0 to 1 dx by x square. Okay, now try to understand what is fx. Fx is equals to 1 by x. If I substitute f0, then ultimately goes to infinity. So from it is clear fx is bounded at x is equals to 0. So that's why what you do, very simple, this is 0, this is 1, this is 1, then what you do? So you have to consider 0 plus some epsilon. So that's why from the definition you should write 0 to 1 dx by x square is equals to limit x tends to 0 plus epsilon, 0 plus epsilon. Okay, so here it should be the different notation. This is not correct representation, so I should write this is the, it should be 0 plus epsilon. Okay, so now here also same. Okay, now you can check that is epsilon limit s tends to 0, that is 1 minus 1 by x, 1 by 0 plus epsilon. What you are getting, that is 1 by epsilon minus 1. When epsilon tends to 0, so that is 1 by goes to infinity. So hence 0 to 1 dx by x square does not converge. So that means you can't get any kind of value. This is type 1. Type 2, a to b fx dx. Fx is unbounded only at b. Only at b. Try to understand the logic behind this. So ultimately, suppose your function is, this is your a, this is your b. Your function fx is unbounded at x equals to b. So you can't consider, then what you do? You have to consider close to b and another point b minus epsilon dash or maybe epsilon. What is epsilon dash? Epsilon is goes to 0. Positive value. Okay. This integral is defined as epsilon 0 plus b, a to b minus epsilon dash fx d, provided a to b minus epsilon dash fx exists. Now try to understand with some example. 0 to 1 dx by square root under 1 minus x square. So what is fx? Clearly the integrand 1 by 1 square root under 1 minus x square is unbounded only at x equals to 1. That means at upper limit your integrand, that is your function, is undefined or unbounded. So we can't consider 1. So that's why you can write 0 to 1 square root under 1 minus x square dx is equals to limit epsilon dash tends to 0 plus 0 to 1 minus epsilon dx by square root under 1 minus x square. So this is nothing but sine inverse x. So limit epsilon dash tends to 0 plus sine inverse x 0 to 1 minus epsilon x. So limit x tends to 0 plus sine inverse 1 minus epsilon x is equals to 0 plus the sine inverse 1. So sine inverse 1 is equals to pi by 2. Clear? Very simple. Just you have to identify at which value in upper limit or lower limit your function become undefined. Okay, so already you know upper in type 1 what you are doing. In type 1 your function is undefined at lower limit, and in type 2 your function is undefined is upper limit. So in case of lower limit you have to add something so that you can come inside, and similarly if your function is undefined or unbounded at upper limit, then you have to subtract something from the upper limit so that you can come within the range of integration. So this is called second type. Okay, very important concept. Now clear? So here in improper integral, just you have to check what type of integration range you have. If your integration range is associated with the infinity, so that means improper integral of first kind. Then you have to check what there are in three variation you have, which one is associated with it. And second type you have to check your function your integration, definite integration with the finite value upper limit and lower limit, but your function is unbounded either upper limit or lower limit, and next is in between. Number 3, this is also very important for you. A to B fx dx, where fx is unbounded only at C, where C lies between A and B. That is, your C lies between A and B. Clear? So first part, first type, at lower limit your function is unbounded. In second type, your function or integrand is unbounded at upper limit. But here in this third type, your fx, that is your integrand, is unbounded at C, at particular point C. This C lies between upper limit and lower limit. So this integral is defined as the sum of a to C fx dx plus C to B fx dx. If you can identify the value C where your function is unbounded, so according to that point wise you should separate as a double integration form, that is a to C fx dx plus C to B fx dx, provided the integral a to C fx dx and C to B fx dx are defined as per above definition. So a to B fx dx you can write limit epsilon tends to 0 plus a to C minus epsilon fx dx, limit x epsilon tends to 0 plus C plus epsilon B fx dx. Now try to understand with some example. So this is also very good example. Minus 1 to 1 dx by x square. The integrand, that is 1 by x square, is unbounded at 0. So that means 0 lies between this. So that means minus 1 less than 0 less than 1. So now you know that this 0 is your function is unbounded. So you can divide the range minus 1 to 1 dx by x square is equals to limit epsilon dash tends to 0 plus minus 1 to 0 minus epsilon dash 1 by x square into dx plus limit epsilon tends to 0 plus 0 plus epsilon 1 by x square dx. So I am here, I try to express directly. If there is a problem you can write like this, very simple, that is minus 1 to 0 1 by x square into dx plus 0 to 1 1 by x square dx. Clear? First of now your function, this function is undefined at 0, so you may write limit epsilon dash tends to 0 plus, that is minus 1, 0 minus epsilon dash 1 by 1 by x square dx plus limit epsilon tends to 0 plus, that is 0 plus epsilon 1 by x square into dx to 1. It's clear? So here I skip one line. So if you want to add this line, you can add it, no problem. So this line, only this line you should add here, otherwise as it is. So you can write directly also, no problem. So simply integration is there, limit epsilon dash tends to 0, that is 1 minus 1 by x minus 1 to minus epsilon dash plus limit epsilon tends to 0 plus minus 1 by x epsilon to 1. So what you have, limit epsilon dash tends to 0 plus 1 by epsilon dash minus 1 plus limit epsilon epsilon 0 plus and 1 by epsilon minus 1. So when you take epsilon tends to 0, so this part goes to infinity, this part goes to also infinity. So ultimately your result is undefined, that is a infinity. So hence minus 1 to 1 dx by x square does not converge or is not defined. Okay. The improper integral a to b fx dx having unboundedness of fx at c, where a less than c less than b is said to have Cauchy principal value. Cauchy principal value. Limit epsilon tends to 0 plus a to c minus epsilon fx dx, and a limit epsilon tends to 0 plus c plus epsilon b fx dx exists finitely. Try to understand. The improper integral a to b fx dx having unboundedness of fx at c, then we can said to have Cauchy principal value if epsilon tends to 0 plus a to c minus epsilon fx dx and c epsilon tends to 0 c plus epsilon to b. Then what is the difference? So in last, what you are doing, so here you are, your function is unbounded at z, then what you are doing, you are taking epsilon dash and epsilon dash and epsilon, you are considering both. But in case of if you consider that epsilon and epsilon, then you can say the value is Cauchy's principal value. Try to understand with example. Find the Cauchy principal value. If you have a question like this, find the Cauchy principal value, that means you should consider both epsilon as a single. Try to understand. Find the Cauchy principal value of minus 1 to 1 dx by x cube if it exists. So from it is clear that the integrand 1 by x cube is unbounded at 0, where minus 1 less than 0 less than 1. So now Cauchy principal value is equals to minus 1 to 1 dx by x cube is equals to limit epsilon tends to 0 plus minus 1 to minus epsilon 1 by x cube plus epsilon tends to 0 plus epsilon to 1 by x cube. So what is the basic difference? Try to understand. So here is the main part. Try to understand. Here your f dash is epsilon dash, you are for Cauchy principal value epsilon is equals to epsilon dash, both are same, as well as just to check minus 1 to 0, that is 1 by x cube into dx plus 0 to 1 by x cube into dx. Then you can write limit epsilon tends to 0 plus minus 1 to 0 minus epsilon 1 by x cube dx plus limit epsilon tends to 0 plus 0 plus epsilon to 1 by x cube into dx. I skip 2 line. If you want to add, you can do this because now you are experienced enough, so that's why your middle point is 0. That's why 0 minus epsilon or 0 plus epsilon. Okay, so that's why I skip. If you want to add, you can add this, no problem. Now limit epsilon tends to 0 plus minus 1 by 2x square minus 1 to minus epsilon limit epsilon tends to 0 plus minus 1 by 2x square epsilon to 1. So ultimately, after substituting the upper limit and lower limit, what you have, limit epsilon tends to 0 plus half minus 1 by 2 epsilon square plus limit epsilon tends to 0 plus minus half plus 1 by 2 epsilon square. Okay, so ultimately when you take common, limit epsilon tends to 0 plus half minus 1 by epsilon square minus half plus 1 by 2 epsilon square, so ultimately your value is coming as a 0. So from it is clear, if you have a Cauchy principal value, so that means you should consider both epsilon dash and epsilon both are same, but if no, then you can consider as a separate. Okay, thank you. Try to solve similar type of question from improper entry.